Today's tutorial is portable stimulus, what's coming in 1.1 and what it means for you. How many of you know what version of the portable stimulus spec is currently the latest? 1.0A, right, very good. That's because 1.0 had some things we had to fix in it, so 1.0A has those fixes. Those of us on the committee have been working very hard for the last year and a half, 2 years, whatever it is, since that came out. And we're excited to share with you some of the stuff that we've been adding to the portable stimulus standard. So that's kind of what today's going to be about. I will start out with an introduction, sort of level setting what is portable stimulus, and I'm going to go through a simple DMA model in PSS 1.0, partly to set up why we've added the things we've added in 1.1, and you'll see how cleverly I do that when we get there. Then Prabhat from AMD is going to talk about memory allocation. This is one of the big things we've added, and so we're going to talk about the problem and some of the concepts we've added to the language. Then Matan from Cadence is going to show how we can use that to create higher level scenarios in portable stimulus. Karthick Gururaj from Vayavya is going to talk about hardware-software interaction realization. So that's another big thing that we've added. And then Hillel Miller from Synopsys talk about how to create system-level models once you have all of that. Then I'm going to come back up and do a really quick summary. I'd also like to give special thanks to Dave Kelf from Breaker and Josh Wrench from Semaphore for their help in putting the tutorial together. Portable stimulus is all about raising the level of abstraction, right? We've done raising the level of abstraction from gate level to RTL, RTL to transactions, and now we're kind of moving up to the next level, right? I think everybody can agree that trying to put together test content is a very large part of the problem that we're all trying to solve here, right? It takes up a lot of time, and particularly as you go from platform to platform throughout the verification process, you tend to change languages. You have to redo a lot of the same work for different platforms. We're trying to eliminate that. So when you go from the block level, you're typically doing UVM tests. Somebody else actually put laborious and error-prone in there for UVM. As you know, I've spent a lot of time on UVM. I wouldn't, laborious maybe, error-prone if you don't do it right. But so anyway, there's a lot of things that UVM can do, but there's a lot of things that UVM can't do as well. When you get up to the SOC level, you're typically talking about C tests. So it's hard to hit corner cases with C because C doesn't really support constrained random, which is really good for hitting corner cases. And then when you get into post-silicon, you're focusing more on kind of diagnostics. You have less ability to see what's going on. So it would be nice to know ahead of time kind of what the scenarios are that you're going to be dealing with. So I think we can all agree that test portability, reuse, and scaling are all really important, but they're all really difficult. At least they were before portable stimulus. And that's kind of what we're going to try to get across to you today. So some of the key aspects of portable stimulus, what we're talking about is capturing your verification intent. So in fact, when we started portable stimulus, there were several people that argued that we shouldn't call it portable stimulus because it's more than just stimulus. There were people that wanted to call it portable verification intent modeling or whatever. That's really what we're talking about here. We're thinking about what is it that you want to verify and how are we going to specify that in a way that we can then use it as we go throughout the process. As you'll see, one of the values here is that we're talking about being able to specify partial scenarios, right? The things that you absolutely want to make sure happen and allow the tool to figure out all of the other things that have to happen to make those things legal, given the rules of the system. We can compose scenarios, so as you go from the block to the system level, you can build system level tests out of stuff that you put together at the block level. And we're going to create from that a formal representation of the test space, right? Given the rules that you specified, there is a certain number of things that can be generated from that, a certain number of scenarios. And that is the test space. And then we're going to go and generate those automatically for you for the test platform that you're talking about using, right? And that can be done for multiple platforms. And we're going to see how we do that, right? So what we're really talking about doing here is separating that test intent. What is it that I want to verify from the implementation? How am I going to actually make that happen on my given platform? Right? And that is a really big thing in portable stimulus, as we'll see. So we're really talking about high coverage test generation across the verification process with much less effort. And hopefully by the end of today, you'll see how we've managed to do that. So at the block level, as we said, we're talking about creating block level, typically UVM tests and sequences based on that scenario intent. And the value here is that, as you'll see, we're going to be easily able to create complex, concurrent, high coverage tests even at the block level. So this will take the idea of UVM virtual sequence and kind of put it on steroids, right? So you're going to be able to really generate a lot of different things, even at the block level, that will be much more powerful than the kinds of things you can do with UVM. at the subsystem level, we're talking about creating operations at that level, reusing stuff from the block level that we did. So it makes it easier to drive these hard-to-predict corner cases to flush out the design operation because we're thinking about things at what we refer to as the scenario level, right? So instead of saying, okay, I want to make lots of things happen here, and I want to make lots of things happen here, we take a step back and we say, okay, for these two things to be doing interesting stuff, we can look at all of those possibilities and make them all happen. And then when you get up to the full system, we're talking about typically software-driven tests, thinking about I/O transactions, still using that common scenario model, but now we're going to be able to flush out system-level functions from a software-driven test and avoiding the necessity of having to really try to fake out, make all the different processors do interesting things. That's just going to happen, right? So the general tool flow is we start with a description of your portable stimulus intent in what we refer to as the DSL, or the domain-specific language. This is a declarative language, and as you'll see, we've added some procedural capabilities to it, but it's mostly a declarative language which allows us to define a scenario model and a set of constraints. Right? A portable stimulus model is basically just a big constraint solver problem. So when you compile the DSL, you get this scenario model. We also have a C++ library that we defined that is useful for generating the same model. Okay? When we talk about C++, you can think of it kind of like the System C library, right? It's a library in C++ whose sole purpose is to do everything that you could do in the DSL to create this model. It is not executable in and of itself on your target platform. It's just a way of defining the model, right? Once you have that model, as I said, it's a big constraint solver problem, so you solve those constraints and you get your solved model. This is the formal model of all of the possible solutions for your constraints and all of the different scenarios that can be generated from the intent that you specified. And then the test generator takes that and generates for you your implementation on whatever your platform is. If you're targeting a UVM environment, it'll create UVM sequences for you. Right? So as somebody who spent 10, 15 years of my career defining UVM, I'm here to tell you PSS is not a replacement for UVM. UVM is one of the target implementations for a PSS model. The other thing that you can do is generate C code from this. It's the same scenario, it's just implemented in a different language. And more importantly, if you have an environment where you have some of the code running in C on a processor model and some of it running UVM sequences in a VIP model, the synchronization between those things will happen automatically. And the solving of these constraint equations can be done either at gen time when you're generating the test. Think about it, if there's 1,000 different scenarios, you'll generate 1,000 different C files or 1,000 different directed tests, basically. Each one will do one of those scenarios. Or at runtime, there are some tools that will create a generic sequence where when it's time to generate the next thing, it goes in and asks the runtime engine, what's the next thing I should generate? And the answer comes back. So you basically get one test that when you run it with 1,000 different seeds or whatever, you get 1,000 different scenarios. Right? Either one works. They're both completely valid. Tools do not necessarily have to do both to be able to be PSS compliant. Just either one is available. The idea is that from that verification intent model that you started with, you have N implementations in your target platform that will allow you to do all of the different scenarios that are valid solutions to your verification intent when you started. This is a list of active portable stimulus workgroup participants. We would love to have more people joining, but this is the group that's been pretty hardcore from the beginning. We routinely get 90% attendance at all our meetings, so it's a really good core group, but we're always looking for new input. So some of the key things we've added to 1.1, we've added some modeling improvements. So being able to capture reusable content a little better. Storage allocation is a big part of that. Prabhat will talk about that. Test realization, we've added a mechanism for defining the register space, and also, as we'll see, a reusable abstract procedural layer, and we'll talk about what that means in a minute. And then we've added some programming enhancements. So it's just sort of general things that a programming language ought to have, like templates, collection types, and other things. And Matan will talk a lot about that as well. So what do we mean by a portable stimulus model? Right? So there's sort of two pieces to a portable stimulus model. The first is what I refer to as the abstract model. And I'm going to spend a lot of time talking about that. This is your verification intent. What does the thing do? What are the behaviors I need to verify? Right? At a very abstract level. Right? I want to send a packet from here to there. I want to do a DMA transfer, whatever, right? At that level, right? I don't want to start thinking about how I'm going to actually implement it because that's the realization layer. And there's a very distinct difference between the two. Okay? This is how portable stimulus can do what it does. We did not try to create a single language that could be used to generate very low-level system Verilog, VHDL, C, Perl, whatever kinds of constructs, because at the lowest level, the semantics are too different. You cannot have a single language that can define all of those semantics. Just can't happen, right? You can ask the Esperanto folks. Instead, what we did was we said, okay, we're going to create this abstract model which we will consciously keep above the level of what are you doing down here in the realization. And in the realization layer, it's for a given target platform, whether you're going to do UVM or C or whatever, you fill in the details in that language for those abstract behaviors. And we'll see how we do it, okay? But this is the magic that allows portable stimulus to be all things to all people, because it's really all things to most people, and then some people have to do the real work in the realization layer. So the parts of a PSS model, we start with an action. An action describes a behavior. Right? I want to do a B to S, whatever that means. In this case, the B stands for buffer. So we have input and output to these things. So we might have like what we'll call a buffer input. So buffers are kind of specialized data structures. So we have a struct construct in PSS, and from that you can define a buffer, which has a certain set of fields to it. You can also define what we call a stream, and we'll talk about what those mean and why they're different in a minute. So actions have inputs and outputs. Actions can also have data fields that can be randomized. So whenever you do a particular action, you're going to randomize the field, in this case size. And you can define constraints about it. You can constrain one field in terms of another. You can constrain input fields in terms of elements of a particular action. And then we also have resources. So resources are kind of the only part of the abstract model that is directly related to the target platform that you're going to be dealing with. In this case, it's basically I have things like a DMA channel, and for my particular application, I have 4 DMA channels available. And that's important to know because when I'm going to start trying to schedule all these behaviors, I can't schedule 5 DMAs in a row in parallel because there's only 4 channels. Right? So that's what lock means, and we'll talk about resources a bit more in a minute. So these are the basic pieces of a portable stimulus model. When we define what is going to actually happen inside of an action, we have 2 types of actions. There's what we call an atomic action, which is the piece that is irreducible at the abstract level and therefore is going to be replaced by a piece of realization. And we'll see what that looks like in a minute. The other is what we call compound actions, which have in it a thing called an activity, which defines the scheduling of the behaviors that you want to have this thing do. So in this particular case, we have a buff-O action that's going to produce a buffer that's going to go to the B to S input. And we can explicitly bind the buff-O output to the B to S input. So you can specifically say this output buffer is going to be directly bound to this input buffer. That means it's the same buffer. So when I put a constraint in one of these activities on the buffer object at its input, it's implicitly a constraint on the output of the other action. Right? So all of this stuff just kind of gets defined throughout the system. The other thing about a buffer is it implies sequential behavior. Right? So the first action has to produce the buffer so that the buffer exists before it can be taken as an input to another buffer. Right? So buffers define sequential action between activities. Right? The stream object defines parallel behavior. Right? A stream object does not get stored anywhere. So when I produce a stream, somebody better be there to catch it or there's going to be a problem. And in fact, the spec defines that if you have one action producing a stream output, it must be bound to some other action that has the stream input. And buffers and streams can be bound between actions as long as the types are the same. And you can also put constraints on flow objects. And if the input says the data field has to be less than 5, and the producer says the output has to be greater than 5, those 2 buffers cannot be connected. Right? Those 2 actions cannot be bound. So we have to make sure that the constraints are consistent all the way through. So once we have this idea of activity, as I said before, the activity is the thing that defines the explicit behavior that you want to have happen. So in this case, we start out with, we have a buff-O action, and then we have B to S and S to B in parallel, and we have B to A, and then we have an AX at the end. Right? So that's the sequential thing that I want to have happen. I can also add in some other things. Right? So there's a select construct. So you can actually choose one or the other branches of the select at random. So now we have two possible paths through this top half of the graph. And we also have this thing called schedule, which says take these actions inside of the schedule and put them in whatever order is allowable given the other constraints in the system. So I can do A1 followed by A2, A2 followed by A1, or I can do them both in parallel. So now I have 6 possible paths through this graph. Right? So this is basically a directed random scenario. Right? So you can think of it in the transaction world as a pretty tightly constrained set of transactions. There's only a few things that can happen. There's still, in just a few lines of code here, several different really complex scenarios. But now we have this idea that from a defined set of behaviors, there are now an additional number of possible scenarios that are valid solutions to that activity graph. Now, when you start getting into things like this, trying to explicitly bind flow objects from one action to another gets pretty complicated. So instead of doing that, what we do is we take these buffer and stream objects and we put them in pools. So a pool is defined as a pool of a specific type of object that gets bound to a set of actions. And then the tool figures out, okay, if this guy's going to produce a buffer and this guy's going to consume a buffer and they're both bound to the same pool, okay, it's going to go from there to there. And this is where the tool comes in to try to figure out the constraints of, okay, if I have an action that's going to input a buffer with a constraint on it, and I have multiple actions that are going to produce the same type of buffer into that same pool, which one of those produces one whose constraints match the guy that I'm trying to hit? Right? So you now have the ability of letting the tool figure out what is the best way to go and put these things together. And that especially comes in handy when you have lots of flexibility in things like this schedule statement. Right? Because does the output of the B to A action go to A1 or does it go to A2? You can't explicitly bind that because it depends on what order you've wound up putting them in. So the pool gives you that flexibility and the tool the flexibility to do that. When you start putting in resources, that adds some additional dependencies. So you define the resource. A resource is another type of a specialized struct. It can be derived from the basic struct type. And it can also have additional stuff in there. There is one field that every resource has, which is called a resource ID. So every resource in a given pool is unique. Each resource has its own ID. So there's a certain number of resources in a resource pool. Right? In a flow object pool, there's however many you need. But in a resource pool, there's a specific number. And that's important because if you don't have enough resources available, you can't schedule things in parallel. So in this particular action, if I have only one channel resource available, I cannot take the parallel option of that schedule statement, right? Because they're both using the same resource and there's only one, so they can't happen in parallel. So resources can be locked, in which case it's a unique grabbing of that particular resource, or they can be shared. So that you can have multiple things using the same shared resource if you want. Then once we have these pieces, we put them together in what we call components. So a component kind of models the different elements in your model. The top level name by default is PSS top. You can give it whatever name you want. You can have subcomponents. So we can group all the B stuff, the top half of the graph in one component and the A stuff in another. The flow object pools and the resource pool can be at the top level, or they can be wherever you need them to be in the hierarchy, because pool binding is hierarchical. So if I have a pool in my PSS top, actions that are in one component can use that pool at the top level to talk to actions in another component. Okay? You can also have a pool in a specific component, so communication can only be within that component, and then you have to have a component outside to go and share it with some other component. Right? So the binding is hierarchical as well. So what's the point of all this? Well, we have the activity that defines these critical behaviors, and this is what defines this partial specification. If you've heard me present on portable stimulus before, I kind of harp on this idea of a partial specification. Right? These are the things that you want to make sure happen, and then the tool is going to infer a set of additional elements to complete the scenario. Right? So if I say I have two actions, I want to take data from the outside and put it over here, and then some other time later I want to create an image out of that data, there has to be something in the middle that's going to process the data as it comes in and turn it into an image, right? So the tool has to figure out, okay, what do I need to do to go from this raw data to this image over here? Right? And the way it does that is by looking at all the other things that you've defined as part of the model. All the other actions that are available, all the different flow object types, whatever resources might be available. And the tool will automatically instantiate these components. We'll look at the components that you've instantiated to understand what are the available actions that I can pick from, and look at the flow object bindings between them to say, right, if I have to have a particular object here, I can only take from an action that's going to produce the appropriate type of object. And then I use the resources to constrain the scheduling options. So basically, my portable stimulus model is a big box of Legos. And my activity defines the critical things that I want to have happen. And then I go in and pick from the Lego box whatever else I need to finish off my Millennium Falcon or whatever it is, right? So here's a quick example to show how that works. So we have a DMA component, has a resource of channels. It has an action that's going to do a mem-to-mem transfer. And I also have a utility component that's going to generate or check data. Right? And I have a data buff pool up there, and I have an action in my top level, which is my test, which is going to do a memory-to-memory test. Right? And in that activity, what I'm going to do is I'm going to do a memory transfer, and then I'm going to do a check data. And we're not going to worry about what those things do specifically, but this is basically what I have. Right? So I have a mem-to-mem followed by a check, and they're sharing the data buffer through a pool. The things available to me are my gen action and my mem-to-mem. Those are the things that produce a data buffer, because the mem-to-mem action has a data buffer input. So I need to figure out what action can I use to create the data buffer that's the input to my mem-to-mem. Well, I have two choices. I can use the gen action, which produces a data buffer, or I can use a mem-to-mem, which also produces a data buffer. But that mem-to-mem has an input of a data buffer itself. So now I have to go figure that out all the way up the top. So there is a built-in limit. You can define the limit of how many levels you want to infer. But basically, from this two-line description of mem-to-mem exfer followed by check data, the tool will then infer however many possible things can happen. And you can imagine that there might be 10 different actions that are available that will produce that memory buffer for you for the mem-to-mem action to take. So now, instead of only 2 at each level, you have 10, right? And it just grows and grows, right? And at any particular point, if there's an action that requires a buffer input, right? Maybe I have another action that requires a different buffer input, right? Or maybe one that requires a stream input. Then I have to infer the action that's going to provide it the appropriate input. And we go all the way up. Now, I may decide that I want to do 2 of these things in parallel, right? 2 mem-to-mems and 2 checks. So now each of those 2 mem-to-mems is going to start inferring lots of things. And now what you have is each of these things is going to be sending data back and forth. And we want to make sure that these data buffers are not going to overlap. And each data buffer represents an area of memory that I want to make sure, if I'm going to take data from here, put it in memory, and then now over here I'm going to take it out of memory and put it over here, I want to make sure that those are not going to overlap. And in 1.0, you would have had to define your own set of constraints and really try to manage all of this. It becomes very difficult. So in 1.1, we've added memory allocation. And that's what Prabhat is going to talk about next. Then we talk about how we're actually going to realize these things, right? And for each target code that we have, we're going to have an exec block that is going to represent the implementation of that behavior, right? So we have 2 ways of doing that. We have what we call a target template exec block. So you can say, this is going to be system Verilog code. So it tells the code generator, I have system Verilog code. And in it, I'm going to put actual system Verilog code. In this case, I'm going to be kicking off a sequence. Right? We use the double brace notation to pass PSS arguments down into the template. And we can do the same thing in C. Right? We also have what we call a procedural interface. So you can actually define a function prototype in PSS. And you can realize that in either system Verilog or C, or any other language that you want that matches that prototype. The only problem with this is you now have to specify the definition of the method in either system Verilog or C. So you're going to, when you go and generate the code, you're going to pull in one file or the other. So your portable stimulus model is the same, because you only have the procedural interface code there. But you still have to implement the same thing in 2 languages. Right? It makes it a little easier to manage things at the portable stimulus layer, but ultimately you have to do the same work twice. So in 1.1, Karthick is going to talk about this abstract procedural layer, which allows you to specify this level of behavior once and generate the different implementations from it.
I'm Prabhat Gupta from AMD. I'm part of the shift left methodology team at AMD. We work with emulators and virtual platforms to drive a lot of shift left methodology for AMD. We think PSS is a very important tool for us in our pursuit for shift left, doing things as early as possible. And so thank you, Tom, for introduction of PSS 1.0, which is probably a 3-day tutorial that he condensed into 30 minutes. Great job. So as you saw, that PSS 1.0, if you don't still understand it all, that's okay. It provides you basic constructs and concepts to model your test space, your scenario, and possibly a portable realization for different environments. PSS 1.1 actually takes a big jump towards usability and enhances all those aspects for you. And one of the major things that we added is memory allocations. I'm going to talk about, in general, just the problem of memory allocation in any test environments, and some of the new concepts that we added to PSS 1.1 for this purpose, and how you can use those concepts in your particular test scenario and modeling. Next 3 slides, I'm going to just talk about, in general, in your existing test benches, what are the different problems that you face. So let's say you have an IP-based test bench environment, and it needs to use memory to do its task, maybe a DMA IP, right? So a lot of time in test bench, you'll have some kind of memory manager modeling a memory, and a test will ask for a memory, and you'll get a memory, right? And then you probably pass it down in a descriptor to your DMA IP or some other IP that's going to consume it and do whatever it needs to do. So this code here, which I'm showing, is using one of these memory managers. It could be in any language, like System Verilog, C++, System C. Now, the problem is you see the source and destination on the top, and you want to create some interesting relationship between those, to do some corner cases. Well, this is a procedural interface. How do you get a source address that has some interesting relationship with destination? Well, think about it. And then if you have a large IP-based test, will this test run out of the memory? How do you manage that? Is this memory manager portable? Can it go to your subsystem, SoC, or even post-silicon? Now, if you go to the subsystem test bench environment, maybe you have 2 different teams doing an IP, 2 IPs, you combine them together. Maybe they manage memory differently. Are they compatible? Can you combine the UVM or whatever testing environment you have to get your subsystem level test? And again, can you create interesting relationship between the allocations? Now, this is a procedural interface. It's very difficult to do that. Maybe you can create a very complex memory manager, and you can ask for, give me 2 addresses that do this, that have this kind of relationship. So it's very difficult. And now, is this portable to your SoC? Now, you are at the SoC level, maybe in post-silicon, in a lab, maybe in a bare metal environment. You write your test. Well, the test is completely different now. You're writing C test, C++ test maybe. You could hard code addresses. You carve out some addresses from your BIOS for your testing and hard code it. You could write a simple memory manager, malloc, and try to create tests. It'll run very slow in your simulation. It'll run slow in the emulation. It will be okay in your post-silicon. But again, how do you create interesting scenarios with this? Is this memory manager portable? Did you use the test that you write at IP level or subsystem level? Anyway, so these are the general problems faced by everybody. People solve this problem, and we've been doing this for some time. So here's the DMA IP that Tom presented in PSS 1.0. What you're seeing is your test space. You're modeling your test space. Well, how many DMA channels I have? This is pretty abstract. Doesn't matter what environment you are in. What are the DMA operations? You can model that in PSS 1.0. This is what Tom showed you. What are different modes? What are different sizes of DMA? All the properties which are kind of independent of your test environment, you model that. Then you can model your test scenario. I want to do a memory-to-memory transfer, again in PSS 1.0. So you have all the constructs to model test space, your scenario, and actually realize your test in C or System Verilog, like Tom said. Now, look at this top up in the code where you have the data buffer, right? This is the data buffer that we are modeling for the data that this IP is going to move, right? So you have an action here, mem to mem transfer, that has an input buffer and output buffer, as Tom said. And when you use this action to create your complex test, somehow you're in that data buffer up top, you're managing that address using constraints. So you could have a test that does 2 transfer. And so you have an activity, you're doing 2 transfer in parallel. You specify in that activity address for the input is equal to twice the address of whatever the relationship you want. Now, look, if you want to do 4 DMAs in parallel, you have to do the same constraint, managing that memory kind of manually, but in a more formal, constrained type of way, but it's still very complex in PSS 1.0. So in PSS, you have your scenario which you described kind of partially, which can produce a very complex random schedule. How do you make sure if you want to allocate memory is still consistent across all your actions that gets realized as part of the test generation? Then modeling the very complex cases with constraint in PSS 1.0 for memory, it can get very complex. A runtime memory allocator might work, but it'll still have the same problem that we saw in the previous slide, that is still procedural. It's hard to get to the corner cases. And so you don't have enough controllability. So in PSS 1.1, after a lot of discussion, like 6 months of shouting at each other, we came up with some concepts and some things to actually use those concepts to solve these problems. So at the core level, we defined a concept of address space. So on the right in this nice picture that I drew, the address space is defined as a set of atoms. I'm not saying what those atoms are. That is uniquely addressable by anything. It could be a string or whatever. Whatever is your way to address that. So that's a generic address space we defined. An address space is then composed of regions, and the region is basically set of atoms within that address space. And you'll later see that the space itself and the regions are characterized by some properties that you yourself define. So we have a generic address space that is composed of regions. And on the left side, this is a more kind of formal definition. The address space is a space of atoms accessible using unique addresses. Agents in system can allocate and access one or more atoms from this space. An address space is characterized by its properties called traits, which we'll learn, and primitive operations over the address space. And we have regions, can be allocatable or non-allocatable. And again, the regions are characterized by the same trait that the address space is characterized by. The general concept that we introduced, the generic address space. It's pretty generic, not really useful. So we define some useful specializations for that. Number one, which we call contiguous address space. A contiguous address space is a space whose addresses are non-negative integer. And this space is defined as containing atoms that are contiguously addressed by a non-negative integer value. Meaning, if you ask for n number of atoms, you will get an n contiguous atoms. Now, what does it mean, atom? Well, so a contiguous address, a common example is your system memory, right? It is a bytes that you can address if it is a byte addressable memory, or it could be a disk drive where you have blocks which are contiguously addressed from 0 to whatever, and that's what is shown here. You could, which we have not defined the type for this, but from the generic address space, you could define a non-contiguous address space. An example could be a routing table in a router. And you could create your own classes and operation on it. It's not defined by standard, but there is mechanism to do. This is the thing that we're going to talk most about in this presentation, which is a byte addressable space, which is a subtype of contiguous address space where the atoms of that space are bytes. And the transparent address space. The transparent address space is a specialization of byte addressable space where the space itself is fully defined in terms of what are the sizes of the regions and starting addresses of the regions are. In this case, the PSS tool has pretty much all the information to allocate memory for you without any external help. So again, a system memory is a good example of that. So how do you use it? Well, we didn't really define a new construct on top of PSS 1.0 language. It's defined as a part of PSS core library. We're still debating on what the name should be for that core library, but we defined this API in terms of existing PSS 1.0 construct, which is a component or a struct or a function. So on the left here, you have the address space component that you can instantiate as part of your PSS model component tree, which will say that this model has an address space. You can have more than one instance of it. An address space is then composed of regions, which is defined as a struct. Again, all these types have a special meaning to PSS tool. So the PSS tool sees those types, it knows it means something, but it's still within the part of the existing language, as part of the language goes. And then you have a claim struct, which is how do you actually allocate the memory. Then you have a trait. Every address space has a trait, which we'll learn a little later. Again, it is a regular PSS struct. And then how do you operate on the space? We have a concept of handle, which is a type that's defined in PSS. And you use handle to operate, for example, read or write in an address space. On the left here, this will be a PSS core library component. And I'm not showing all of the code here, just the contiguous address space component on the left. And you have a function there, add region to add regions, and you can say if it is a byte addressable space or not. We made conscious choice to have this by default byte addressable because that's what we think is the most common use cases. And then again, you have a transparent address space region where it says that only you can have a transparent regions added to this. That means the regions know its size and starting address. On the right, this is how you use the address space, meaning in your PSS component tree, which is your model of your test space. You can instantiate these address space components. And in an exec init block, you can instantiate regions, initialize them, and add to your address space. You can have more than one address spaces in your component. Now, address space trait. So there's a lot of interesting ways where you can test your memory or anything that uses memory. You could have memories with different caching attributes or security policy. So in PSS, we have defined a way where you can associate a type as a property for a given address space. On the right here, you see this struct called memstruct. This is just a regular struct where you have two attributes, a cache attribute, which is probably an enum, and security level, which is also an enum, and you randomize it. On the left here in the code block, you see the PSS top. We have two address spaces instantiated under it with the trait type. One is the mem trait S and FB trait S, which is a frame buffer. So if you have two distinct memory spaces in your system, maybe a graphics core inside it, which has a local frame buffer, you can instantiate two address spaces to model that. And you have these traits. So in the exec init block on the top left, you see we created two regions and setting these properties for those regions. For R0 and R1, the cache attribute and security level, and then we are adding them to the two spaces that we created here. So for address space region, again, these on the left, the types are in the PSS core library. This is how you create a region and add to the space. Again, regions are templated by the trait type. This is an important point that I forgot to mention, which is that PSS 1.0, we have defined templates. So you can have types with a template argument. So in this case, the space and the regions are templated by the trait as part of your PSS model. This is just an example of a trait. This is your system memory. Let's say you have a trait with cache attribute security, and maybe is it an MMIO. So all these yellow things are different regions that you added with different, the trait type is same, but different value of trait. It could be on the left, probably an SRAM with a write-back cache or security policy 0, and things like that. And in the gray boxes you're seeing is that's the memory that you allocated with the PSS claim struct that I've shown earlier, the API. And those arrows are actually handles within that claim that you can use to operate on that memory. We'll see that later. Now, how do you use this address space and region that you just created? Well, you claim a memory in the declarative PSS model in your activities or actions by creating an instance of this address claim S struct. That's the core API that we have defined. So once you create that instance, the act of creating that instance allocates a memory in PSS. These claims are pretty opaque, meaning you create that instance, and you don't really, unless you're using a transparent address space, you don't really know much about it. And that's on purpose, because we want to make sure that we can keep the allocation as abstract as possible for as long as possible, so we can realize a test. Realize means actually generate the test for a different platform that we know nothing about. So most of your model will still remain portable. Now, when you allocate a claim name, maybe you have an action that needs memory, and you allocated memory by using this claim struct as part of that action. Well, how long that memory is valid for? So the lifetime of allocation is a very important concept. There's a lot of details on that, but generally the lifetime of memory is the lifetime of object that allocates it. In this case, if it's an action, the lifetime of an action decides the lifetime of that memory claim. And there's ways to extend that lifetime. This is simplified DMA operation, DMA model, and it has an action mem-to-mem transfer. And then you see we have this address claim struct that we are creating, just the fact that it's in the action, and you have a source and destination memory. Now, when this action gets used as part of some bigger scenario, the source and destination memory gets allocated by the PSS tool, and they will be unique by definition. You can use constraints on those claims. For example, in this case, we are saying the size of the source and destination allocations are same, which is the size of this rand variable size that we declared here. So that's how you use it. So this is one way you create this instance of the address claim S inside your action. Another way is to use the buffer object or any other flow object to allocate memory. Now, in this case, this data buff object, we have the address claim struct, which means whenever that buffer is created, you actually claim the memory. So in this case, this mem-to-mem transfer inputs a data buffer and outputs a data buffer. The output portion of it will actually allocate the buffer, and that buffer will be valid to the next action input, whichever is inputting this buffer. And you see that source, you can again do the constraints to make sure the source and destination buffer sizes are the same. And this is just showing that once you have that, you can create your PSS top, allocate address space, instantiate your space, create regions into it, and that will complete your model. Now, in your system, a very complex system, you could have many different distinct memory spaces. The common case is a graphics chip with its own local frame buffer and a system memory too. So if you have an action for an IP, and it's allocating memory, how does it know which space do I go and allocate memory from? So this is where the matching rules that are defined comes into picture. So let's say the DMA 0 component here, which is kind of representing your one DMA IP in this instance tree of components of your input model. And that action of the DMA is actually claiming a memory with certain trait. If you go back here, you'll see the data buffer claim object has a template type mem trait S. So the claim is actually asking for a specific type of memory. So the PSS tool will go up in this instance tree and find a memory address space component that matches that trait, and if it has that region with that particular value of the trait, it will allocate memory from there. So it basically walk up and find the matching claim in the instance hierarchy. And there are more details to it that will come in as part of the spec. Now, those were the main concepts. Now we're going to talk about, well, how do we actually, we allocated the memory, now how do we use it? So this is the same picture. We have the memory with different regions and then the claim, and now we're going to talk about this handle, which is this arrows here. So what is a handle? So handle is an opaque representation of a location in an address space. It's like a pointer in C or C++. Primitive actions functions use these address handles to read and write data to and from this address space. We have core library functions that we have defined only for byte addressable memory, contiguously byte addressable memory, that you can use to write your input model. And Karthick will talk more about it, but you have the whole procedural language to completely create your test in a portable way. Handles, again, similar to like the claim, can be declared inside objects or inside actions. So on the left here, we have defined an address handle T, which is the type that denotes its address handle. And we have a bunch of functions that you can use to obtain a handle from a claim. So the idea here is in your exec body, which is kind of a procedural code, you can get a handle from a claim and then operate on it. So you can get a handle from this make handle from claim function. And then in your exec body, if you want, you can get the absolute address, resolved address of that claim using this address value function over the handle. Here's the use of the handle. In this case, I have on the top the data buffer object. Now it has a handle. And this particular DMA action is called chain transfer, is actually allocating a memory, this address claim S struct. And then in the post solve, we are getting a handle of that claim and putting that into the destination. So what happened was this action actually taking a source buffer as an input, which is it's getting a memory that was allocated by somebody else. It doesn't care. It needs just a handle. And it's allocating some memory and passing the handle through the output. And that's how you basically, the lifetime of this, the memory claim here gets extended to the action that's going to consume it. Now here you see this write 32 in the red. That's how you operate on the contiguous byte addressable memory using the standard API that we have provided. And this code is pretty portable across all the realization platform, your IP, SoC, or post-silicon. Important thing is these are only defined for the contiguous addressed byte addressable space, contiguously addressed. You can read and write bit 8, 62, 32, those sizes. You can have an array of those, or you can read and write structs, PSS plain structs, fixed size structs, and you can read and write an array of those too. This is an important use case that Karthick will talk more about in procedural interface. So you have a DMA IP or some other IP. Generally, these IPs expect a descriptor that some program or driver sets up in memory in a very fixed format, a very fixed layout. Now, we have defined an abstract kind of address space. Then how do we set a particular descriptor in that memory that's still being portable across all the platforms that we are targeting? So if you define a descriptor, a lot of time you have different, for example, for DMA, you might define what's the mode of the transfer is, what is the size of the transfer is, and what's the next descriptor in that descriptor chain, meaning you put a pointer inside your descriptor for the next. What is the memory buffers it's using, source pointer, destination pointer. So this information needs to go in a descriptor that goes into your memory, and we need to have a way which is very abstract. So the whole descriptor programming sequence stays portable, meaning you can target it from different platforms. Not like PSS 1.0, where you have to manually create those in different languages. Now, what is the problem with that? Well, now we have the memory space. We know we can get a handle into the memory space. How do you define a descriptor? Well, you got to put that handle inside your descriptor. But the handle is pretty abstract, opaque. We don't know what it is. Well, but for descriptor, you need to know exactly how many bits you want to put in that descriptor struct, because it's a very fixed layout that an IP is expecting, right? I mean, apart from that, the struct could be, your IP could read it little endian, big endian. There's a lot of details how you define a struct. And we have defined all the ways where you could take care of the endianness of the IP and how you use a handle of a memory inside a struct. So we define a concept of packed, which is again a core library type that we have defined. If you derive a struct, PSS struct from a packed type, you will get a packed representation, and it will have a special meaning inside the address space that you have defined. Now, what is this sized address handle underscore S32? What does that mean? So a lot of time, if you have a DMA IP, a lot of time it will do a very aligned transfers, like 4-byte aligned or something. And sometimes it will expect that you put that address, if it's a 32-bit address space, you ignore the 4 bits and you only put the bits that it needs. So this is the way we have defined you can do that. If you take an address handle, this source and destination and next descriptor here are handles. you could define that whatever the resolved address is when the PSS tool is generating the test after all the memory claim, resolution, solving, whatever it needs to do, get the 32-bit from that address. Well, and at the bottom here, the bottom text box is actually defining that in more detail about that. You can specify that I want first 32-bit or first whatever number of bits from the handle. So again, this is an important concept that you could have an abstract space. You can operate over it abstractly, and you can define a descriptor which is abstract for your device and write your programming sequences for that device in a very abstract way. And all the details are defined. It's coming up in PSS 1.1. So just to recap, this was your test space model and the scenario model for your IP. And you use at the top data buffer object with address, and you manually constrain that to manage the memory inside your bigger scenarios. In PSS 1.1, you do write a little more code, though, but your mem-to-mem transfer action here knows how to manage memory, and the PSS tool will help you with that. So if you have an SoC with 10 DMA IPs instances, and if you want to run 10 DMAs or 50 DMAs at the same time, all you do is, like Tom said, in a parallel block, you set 10 mem-to-mem transfer. And because you have done this extra work here and PSS 1.1 supports this allocation methodology, you don't have to worry about it. So anybody who's writing a tested SoC, just say, OK, 10 parallel of this. I don't care. And the memory will be consistent and allocated and reused whenever you need to. So now memory is allocated through the object that we have defined, either create an instance in a flow object or an action. Every allocation is unique. Allocation intent is portable. Lifetime allocation can be extended. There is a complex example that's part of the spec, or a user guide maybe will come out. So the memory, you could define many different kind of memory address spaces, but byte addressable memory and operations are part of PSS 1.1. Your model is now very abstract. Allocations are consistent across randomly scheduled actions. And with the portable procedural interface that Karthick is going to talk about later, you can truly write the portable code. And you could model all the interesting relationship between different source and destination in PSS 1.1 very easily.
This part is going to talk about something completely different, following on the lead from Tom, who told you how you take the modeling elements and you put them together to compose ultimately your test intent. So you build up towards some specific use case, some specific intent, and the essential construct here is actions put together in some activity, in some control flow, in some schedule, in some data flow, and then you can encapsulate that in a higher level action, and that becomes a building block for yet higher up descriptions. I'm going to talk about that aspect of the language, which is more how you ultimately achieve your test intent. We have quite a number of enhancements for this purpose in PSS 1.1. There's a common theme here to these enhancements. I actually broke it down into 3 steps leading up to a certain use case example, something more realistic, more real life. But in each of these steps, I'm going to pose a problem and motivate a new construct, motivate a specific enhancement, and then I'll tell you about the construct and how it addresses the problem. Right? So that's how I structured it. But what you need to keep in mind is that there's a common theme here. Right? Even though these and a bunch of others are independent language enhancements, there's a common theme here in the bigger picture is, even though none of these are a fundamentally new modeling concept, right? Unlike PSS 1.0, where we came out with a whole zoo of concepts, these are not fundamentally new concepts. These are not new semantic primitives. So in a sense, you could pretty much express the same things in PSS 1.0. You'll see that you could spell out the same scenarios with 1.0. The purpose of all of these is to enable you to be able to express these in a more generic fashion, in a more reusable fashion. So you can use these constructs now to not only hit on certain test cases, but also to encapsulate these in reusable building blocks. So now with PSS 1.1, we think we enable you to capture content libraries for real for the first time. And this is key, of course. So even if in principle you could hit on the same intents with PSS 1.0, you would still have to spell it all out. Whereas now you're able to capture it in a more generic and reusable fashion. So keep that theme in mind as I walk through these different constructs. So first step is about composing concurrent activities. So again, back to that same old DMA example that Tom showed and Prabhat referred to. We had that modeling element, the memory-to-memory transfer actions. And then pretty much, one of the first things that you would want to do is schedule a bunch of these in parallel, right? And the DMA engines typically can handle a number of transfers in parallel. And Tom had that resource pool representing the number of available channels. So each transfer is going to lock one channel, and there are only so many that you can do in parallel, but still you do want to schedule such in parallel. That's one of the essential verification intents that you're going to have even at the IP level. So doing 3 in parallel is a no-brainer, parallel block, and then do 1, 2, 3. But then a very natural thing you want to do is utilize all of the channels in parallel. DMA controllers typically have 8, 16, 32, 64 channels. What are you going to do? Are you going to hand code 64 or 32 lines of calling a transfer action? That's kind of nasty to write. But what's worse, it's that you cannot read the intent off of this code, right? Of course, I call it with a meaningful name. I say, the intent of this action is to utilize all channels in parallel. But it's not explicit in the code. And the worst part is that in the next generation, I'm going to have 64 channels, right? And also in different configuration, I have a different number. And so do I really have to hard code it for each case? So clearly, this is not practical. So you get the sense that it's doable, just not practical. That's where we throw in the replicate statement, because what you really want to say is simply replicate this statement 31 times, or n number of times, or num of channel times, right? So simple, but you simply couldn't do it in PSS 1.1, not in this way. So replicate statement, and then the number of times. And just like with an iterative construct, it's useful to sometimes make reference to the iteration index. So I can do that too. For example, if I wanted to just utilize the even numbered channels, I can do that with reference to the index variable and kind of what you would expect from an iterative construct. OK, so I hope I gave you the problem, motivated the construct. Now I want to tell you a little bit more about the construct. That's its syntax, replicate, and then the count expression. Optionally, you specify index variable. I am not going to talk about what you do with this label array. It's important, but that's the 3-day tutorial. This is a statement or statement block that's being expanded in place, right? So how would you interpret this activity? Easy. Literally take this block and copy paste it 3 times. And for each instance, you plug in the iteration number. So you saw that under this parallel scope, there was this replicate and another statement, right? So after having expanded in place the replicate statement, you actually have 4 parallel branches, right? So you're describing the following activity. The sequence AB 3 times in parallel, each with a different parameter value. And then 4th branch is that last statement, the C, right? You get the picture. The leftmost block is equivalent to the middle code block, right? All you did, copy-pasted. A macro-like thing, if you will. Another way to think of it is consider how similar these two look, repeat and replicate. I'm having this up for you to not get confused, because a repeat is truly a loop, right? So if I had to represent it in an activity diagram, I would represent the fact that there's a sequence AB that's being iterated over in a loop sequentially. So there's a condition that at the termination of the loop, it's going to go on so long as I is less than 3. You still see the key thing is that under this parallel statement, there are only 2 branches, the repeat and the do C thing. The replicate is not a loop. It's a macro-like thing. We call it activity construction statement. So it literally transforms the syntax tree of the activity. In this case, it's under a parallel statement, means that the iterations, so to speak, execute in parallel. Right? This could be under a sequential block, and then they would happen to be executing in sequence. But that's, again, just because it's expanding in place. It's transforming the structure of the activity in place in whichever context the enclosing statement is. Now I'm going to kind of shift focus from just considering functionality of the DMA controller itself to something that's more systemic, if you will. So for my present purpose, I'm looking at operations that do memory access, maybe not even generically, but actually moving data from one location in memory to another. And for that purpose, a DMA transfer is one such operation. A CPU performing a memcopy is another. I could have a whole bunch of other memory-to-memory data processing operations. And I'm going to just randomly select between them because maybe they're symmetric from the point of view of memory access. Okay? So now I have this nice little parallel memory access activity where there's any number of either memcopy or DMA transfers executing in parallel. Right? So it's kind of a memory fabric building block. Now, as I consider maybe faster platforms, right? Maybe I had simulation in mind initially, but as I consider faster platform, I can hope to squeeze many more operations because I have a lot more cycles. So pretty much the same test intent, I would now want to leverage the more cycles I have for a longer kind of scenario. But it's still essentially parallel mem access sequences. So instead of just selecting one operation, I'm selecting a sequence in each of these parallel branches. So you see, the only thing that I threw in is that repeat, and I have an attribute for the loop count, the inner loop count, right? Maybe it's a little sketchy, but I think of it as similar intent as what I started with. And maybe I'm thinking about this applicable to faster platform or certain situations. So I took something and I generalized it. And I made it applicable to a broader range of cases. It's still kind of the same thing for me, but more broadly applicable. However, that's where I get into what you might call the control knob dilemma. Because this is just one, maybe not a very striking example, but I'm going to have a whole bunch of additional attributes that serve as control knobs for these further generalizations of this otherwise same building block, or building block with similar intent. And as I do this, I don't want to sacrifice the simple case. I don't want to compromise the simplicity for the mainstream, right? So I still think of the left thing as the mainstream or simple case, and the right thing as something more specific. So the one thing that I'm missing here is a way to specify a default. I generalize something with more controllability, but still want to be able to fall back on the simple or mainstream case. And that you simply couldn't do in PSS 1.0. And the reason you couldn't do it is because these parameters of these compound actions, right, of these, I should say, mid-level actions, are just rand attributes, and they get randomized. And unless you constrain them, they will get randomized in the full domain. And for some purposes, I very much do want them to be randomized. But for many of them, many of these control knob, little control knob things, I want to have a default. So now we do. We have a default constraint. A default constraint is a very restricted form of constraint where you just designate a specific attribute and associate a constant expression with it. So The analogy you could have in mind is just how you initialize a non-round attribute, right? You give it a default. And so now you can give a default to a round attribute. And you would have to disable that default if you wanted it to randomize or to resolve to something else. Let's walk through an example that would clarify things. Here's my struct, and it has two numeric attributes ranging between 0 and 3, utter1 and utter2, and place a default constraint on utter1, so it's by default 0, and utter2 can randomize, but there's a constraint that it needs to be greater than utter1. Now in my action, I instantiate my struct multiple times, and let's see how I constrain it. So first instance, just as is. Then, of course, utter1 is going to resolve to 0 because of the default constraint. Utter2 is going to range between 1 and 3, just to be greater than utter1, right? Simple. Now for the second instance, S2, look at how I put a different default on that same attribute. So I'm overriding that default for this specific instance. And so, of course, utter1 is going to resolve to 2 because of that new default, and utter2 would have no choice but to be just 3, right, to be greater. And then the third case is even more interesting. I'm disabling the constraint on utter1, whatever it may be. I'm disabling the default, sorry. And then I'm placing another constraint on it. So not only is the default disabled, but there's a different constraint on it. So now, because it needs to be greater than 0, it randomizes in its full domain. But because these two attributes, it can only be either 1 or 2, and utter2 can be 2 or 3 respectively for it to be greater than it, which you cannot in system Verilog. But of course, you can override it in a subtype, but you cannot disable a specific instance. And that's the key here. And so it would be a hard constraint until you disable it, and then the attribute would randomize in its full domain, which brings me to the third difference. A soft constraint is always there. So it will always bias. It will always bias the results unless it happened to be completely ruled out by other constraints. I don't want that. I want a default, but I want to still be able to randomize without bias. So I'm just saying all that because soft constraints have been used in system Verilog and other constraint languages to capture defaults, but they're very useful for other purposes, not as good for capturing defaults. And what we needed for this problem is simply defaults. Now I have these more generic mid-level behaviors that I'm hoping would be applicable in many cases, but how would I apply them to more specific intents? So back to the 3 transfers in parallel for my first slide, right? That's sort of generic still in a way. And now I have a more specific intent in mind where I want to specifically do large transfers in parallel. And for me, large is greater than 1K, whatever. Right? So, hey, no problem. I'm reusing that building block, but constraining it, in this case, constraining the sub-actions, I can do that happily, right? So very useful 1.0 construct is simply being able to constrain sub-actions from above. But clearly this becomes completely impractical for anything more complex than that. Right? Because just consider nothing too fancy, our parallel mem access. How did it look? We had a repetition of selection under replicated branch in a parallel. Something fairly straightforward, but how would I ever reach down into all of the DMA transfers to constrain them such that they're large? I'm going to reuse that parallel mem access building block for this now more specific intent of exercising large transfers, or maybe large transactions in general, right? But even if I did know the path down to these sub-actions or second level or third level sub-actions, even if I did know what the path is, I would never want to hard code it, because then I would be coupling my top level intent with the specifics of how possibly library activities are structured, right? Non-starter. Now we have constraint for all, a new constraint form, and it just does that, exactly that. It's for all instances of a mem-to-mem transfer action in a certain subtree, apply a certain constraint. Maybe I want to do something similar for CPU mem copy, right? So abstracting from how the activity is actually structured, I'm placing a constraint on all elements by type. So binding a constraint by type in a certain context. And it's going to propagate all the way down to all instances of this type. So here's the syntax, just like you saw. You need that iteration variable, for lack of a better term, and then, of course, the type. You're going to bind the constraint by type. Otherwise, it looks very similar to a for each constraint, right? It's very similar, actually, to a for each constraint. But the for each constraint you place on an explicit array. Here you place it on kind of an imagined array, if you will, or an imagined collection of all the instances of a certain type in the subtree where you're at. Let's do this interpretation exercise. Action A with a round attribute. There are two A's in parallel under B. And now in my higher level action, I'm going to do an A and a B. But now I'm going to constrain all of the attribute of all of the A's, right? And I want to constrain them against my own control knob, right? So it's contextual. The interpretation would be just to place a constraint on each of the paths to an instance of that type. So again, in principle, I could do the same in 1.0. In practice, I could never do the same. A word about the for all scoping. I think it's important for the purpose of applications. Again, imagine a higher level action where there's a sequence scheduling an A and a B, and then again scheduling an A and a B. My point is that you can put a for all constraint in different scopes to direct that part of the activity in some other way. So I have here two limits, right? So the limit for the phase 1 and the limit for the phase 2, right? And so because of this scoping property of for all constraint, I can use the same building block in different ways, even within the same scenario, right? So on that subtree, I'm putting one limit. On that other subtree, I'm putting another limit, but only on the A actions, right? So this scoping is another key property that lets you pull in content and direct it for specific purposes overall and for specific parts of a scenario. Okay, now I promise to bring all of these threads together into an application that you can relate to. Imagine that you want to hit on a certain memory controller from multiple agents, multiple masters. Maybe it's a complex NOC or fabric design, and you have any number of different agents that you want all to hit on the same DDR controller, right? And it would stress it and maybe get it to certain corner cases or certain traffic patterns. Prabhat told you about the notion of a trait, of an allocation trait, and suggested that you'd have an allocation struct on the buffer object, which the DMA transfer action, inputs and outputs, the memcopy action, inputs and outputs, all of these have buffer objects, and the location in the address space is managed by these new memory allocation capabilities. And so if I have not only the SRAM DDR distinction mapped out on my address space, but also the identity of the controller mapped out as different regions, they could be interleaved, like in this picture, right? The 4 controllers that I have happen to be interleaved. And so if I have that set up like Prabhat told you, then all I need to do is maybe pick out a controller and then just do my same old parallel mem access action, constraining all of the buffer allocations to just memory of kind DDR for controller 0, which I happen to pick out, or controller 3. So, and I'm also randomizing the loop count, right? So look, just maybe 5 lines of code for capturing the test intent, quite complex. Again, that same activity with concurrent memory access threads, all together hitting on the same poor DDR controller. Not a very simple test case to implement, but I just did that with 4 lines of code. And the beauty about these lines of code is that they speak for themselves. You be the judge, but to me, this is a very natural concise way to express the intent, almost face value.
So I don't really intend to comprehensively cover all the features in PSS 1.1. I think the more important thing here is that you get an appreciation of what is possible with this rather than maybe how, because how you can always look up later. So let's look at this. The box on the top, the abstract model, is more what we have been talking about so far. And that's really the domain of algebraic constraints and activity statements and so on, right? And what it all boils down to is, at the end of the day, from the test intent, a tool will kind of explode it maybe into a sort of sequence of leaf level actions, because that's really that kind of bottoms out there, right? And the test intent basically determines what leaf level action gets scheduled, maybe when, and whether there are many going to happen in parallel, what will be the inputs to these actions, and how the outputs will be connected to another one, and so on and so forth, right? So that's what the abstract model is about. But that still doesn't talk about what API, maybe if you're trying to test some software, right? You finally need to call the functions in that DUT, right? So which function will get called in this leaf level action, right? That is not covered in the abstract model. That's really the domain of what we call as test realization. And that's where we talk about the execs, exec body, exec pre-solve, and functions. This is nothing new. It's been there in PSS 1.0. And 1.0, like Tom mentioned, provides two ways to specify your test realization layer. One is called target templates, which very loose analogy is, if you're writing code in C, you might have used an inline assembly block, right? You can actually in C, I don't know if, okay, maybe some of you are familiar, you can actually specify a sort of a literal ASM block that should go into a function body. When a compiler looks at it, it just spits it out, whatever is inside. That's essentially how maybe target templates work. Another way is what we call PI, procedural interface, which kind of works like, in C you call a function, and it so happens that the body of the function is implemented in assembly in maybe a different file, right? So that's the two mechanisms that are already there in PSS 1.0. Now what does PSS 1.1 add on top of this is maybe how generally a C code gets translated to ASM, right? So what you have is a compiler that actually parses and transforms it to a target specific assembly, right? So that's the kind of feature that we have added. So from the abstract model, what you can generate are, let's say, the scenarios. Then specifying the test realization layer, you can actually generate what I call here as a device driver. I'll come to why I call it a device driver soon. So this could be for a specific environment, like could be for an RTL simulation, in which case maybe the entire code is in system Verilog. Or maybe you are looking at a different environment where you need to generate some sort of C code. This is great because in PSS 1.0, you'll have to kind of need to specify this inline target template for each environment differently, right? But here, with the additions what we are talking about, a tool can actually generate the required low-level, the last mile connectivity, let's say, to the DUT. The low-level functions can be generated from the same representation of the sequence. Just like you can generate scenarios for different environments from exactly the same abstract model, you can also generate what we are calling as a HSI, hardware software interface realizations for different environments from the same specification in the test realization part. So that's basically what 1.1 adds. So what does it really add to in terms of the language, right? We can specify some sort of procedural code as a part of your test realization, which is part of the language syntax itself now, right? So I'll show you examples later. As a part of this sequence, as part of this procedure, you can do many things. As you can expect, you can maybe have loops, you can have conditions, you can have also be able to read and write to the, let's say, the registers of a DUT, okay? As Prabhat covered earlier, if a certain DUT, we have been talking about the DMA controller so far, if it can handle some sort of descriptor in memory. So many, like a scatter-gather DMA, requires that a software sets up some sort of a table, descriptor table in memory that the DMA will reach out and decide what it needs to do, right? So the descriptors in memory needs to be set up by, well, I say software, but it's really the test code finally, right? So how that needs to be set up. So even that can be specified in 1.1. So actually the use case or the sweet spot we kind of started this whole, let's say, series of enhancements is to finally be able to specify some sort of a programming sequence for a, let's say, a DMA controller or any other peripheral in an abstract way, which a tool can transform to whatever code you want. So that's really the sweet spot. You can use it maybe for other purposes as well, but for today I'm going to look at this as a use case and go into it. Again, right, I kind of covered this already, so I'm going to go through this a little bit quickly. This is already there in PSS 1.1, so you can have what are called target templates, right? So this is really like inline code snippet that you can put in, or you can have what is called a procedural interface. You could specify, let's say, for execs, you can have like a brace and specify some constructs inside which a tool will transform, but there are a lot of restrictions on what you can do in 1.0. So yeah, you can basically only do assignments, function calls, and use of super. So no branches, no repeats, none of those facilities are there. So what 1.1 adds to this is, if you can see on top, you can actually define, let's say, the body of the function. Similarly, you can define the same for execs, and you can now do a lot more. So for example, if you have like some sort of a sequence function you're trying to write, which you want to sum up all the elements in an array, excluding some cases, right? So you can just go ahead and write this sequence up. It looks pretty much like C, and it is also very similar to the activity constructs that you're already kind of familiar with. So all the activity constructs can have some sort of a similar semantics here as well. There are a few changes or enhancements specific to this procedural constructs, like conditions. You can have a break and continue. You can't do that in activity statements, and you can have like a return, which again, you can't do this in activities. You can declare variables, you can have nested blocks, and I mean, the example doesn't show many other, like you can have function calls, you can have expressions, right? I think it's there. So you can kind of specify that result is result plus element and so on. So the point is, a tool is going to look at this and generate the body of, let's say, device programming for your environment, be it System Verilog or be it C. And again, when I say C, it's going to be pretty different for every environment, right? So it can handle all of that. What is not there at this level, because that's really at the test intent level, is support for randomization. Okay, so now we are going to kind of walk through an example of how this whole thing is going to look for a DMA controller. I just took a ARMS prime cell DMAC as a reference. Yeah, this is just from the data sheet, the sequence in which you need to do things to finally program a DMA transfer. So the actual IP supports scatter-gather DMA, and it does all that, but I'm kind of simplifying the example to kind of only handle, let's say, a single transfer from a source to destination. So this is like a necessary scaffolding that we have. The kind of a brownish golden color you can see is our special constructs that a tool understands how to deal with. And again, we have seen this already in Prabhat's section. So what you see here is, if you see this, there's a DMA component. This mem-to-mem exfer is a leaf level action, which finally in its exec body is calling a function, which is here, right? Do transfer, and it gives all the necessary parameters, the channel number and source, destination, address handles, and the size for the transfer itself, okay? And in 1.1, this is possible. You can do this in 1.1 as well, except that the do exfer function needs to be defined by the user directly in C, for example, right? So here we are going to see how it can be done in 1.1. So firstly, what we will do is we are going to extend the component DMAC that we saw on the previous slide. And in this extension, we are going to create instance of all the registers from the test bench side. It's really a mirror model of the registers, right? So that's what we are going to create. And we are also going to define the doXFR using these registers. Okay, so just a note on how the registers themselves are defined. So this is something that a user typically won't do by hand. It will be maybe auto-generated from some specification, maybe IP exact or system RDL. So I'm not going to go into the syntax, but I'll just tell you what you can do. You can, if a DMA controller has got like 10 registers, you can define all of this by, you can specify the name, you can specify, if the register has got like bit fields, you can specify that. You can specify the offset of each register and a few more things. You can specify NDNS, whether the register is readable, writable, and so on. The idea is to model those properties of the register which are relevant from the use case we have in mind, which is basically specify a programming sequence for the peripheral. So the registers themselves are specified as a component, as you can see here. And when you create this register component, you're going to give it a few parameters. The first parameter is type, which specifies what is the value type that goes into the register, right? If it is a 32-bit register, the type could be a bit 32, for example, right? But if a register has got bit fields inside, it shall be a structure with all the bit fields inside. So it's really a type that represents the values that reside in the register, let's say, if you want to think about it that way, the value that you can write into a register or read from a register. Okay, I think it will become maybe more clear with an example. And then you go ahead and kind of create instances of these register components in a group, a register group. And you can have nested register groups if you want to model a hierarchy, for instance, like that. So finally, as you kind of keep aggregating this, you will kind of end up with top level, let's say register group. And that gets associated with address handle. So again, I'll show an example. Here is a sequence of programming the DMA controller. So it kind of maps well to the bullets I showed you earlier on what is from the data sheet. I really don't want to focus a lot on the syntax here, but if you see this, what's happening is we are clearing the interrupts by writing some value into these registers. And then we're setting up the channel by setting up the source address, destination address, and parameters. Finally, we enable the channel, which actually triggers the DMA to perform the transfer. And when that's going on, what we are going to do here is to wait for completion by essentially we keep polling. In this case, we keep polling for certain status register to kind of get set. If you see some of these register definitions, it would look something like this. You can see here that there is a struct which captures the type of the value that can go inside the register, right? And that is used as a parameter here. And in TCCLR is really an instance of this component, but you can see there is a function called writeVal that's getting called. So the way that works is the base class, redC, which is like a special base class in the sense that the implementation of which is supposed to be provided by, let's say, a PSS vendor, tool implementation, right? So what the base class redC will have are essentially functions that can be invoked on the instance of a register. In this particular case, you can do a writeVal and you can give the entire, in this case, it's a 8-bit or some 32-bit value can be provided. This is a slightly different example where the value we are writing is not a plain 32-bit number, it's an instance of a structure. So you can see here, you can create an object of a structure, you can set all the bit fields that you want to do, that you want to kind of update. And then in like one shot, the register gets updated with the contents of the structure. This is the last part where instead of write, we are calling a read. So you're kind of deciding to break out of the loop when certain condition occurs. Okay, so we have kind of defined these sequences for the peripheral. So the question is, how does it map to maybe at a system level, right? So here I'm assuming that we are really want to verify system level which has many maybe peripherals. I keep saying, you instantiate a DMA controller, but again, I wanted to be clear that I'm talking about the test side, not the design side, right? So maybe I should keep saying you instantiate a verification component for a DMA. Maybe I should keep saying that, but I don't. But that's what it is. So you instantiate these components and you create an address space that represents the placeholder for defining the regions in the memory. And you kind of add the regions to that. That's what you see here. And here we are basically choosing to do a non-allocatable region because you don't want your claims to resolve into this. Yeah, that's it. You just go ahead and do this for all the peripherals. And the tool magically converts this to all the sequences with the correct address offsets added and so on. So the first bullet is just what we talked about. Yeah, there is just on the second point, typically these registers can kind of explode. You might have designs with many millions of registers. So the language has got syntax that lets tools optimize the, let's say the internal representation that they need to kind of manage. While the slide showed only DSL examples, we have equivalents for PSS C++ as well, including all the procedural constructs. So you can define all of that.
I am going to now talk about two topics. One of the topics will be about how this works in practice, how the portability works in practice. And one pattern we'll be looking at is moving from block level modeling, DSL modeling, to system level DSL modeling. Specifically, we will take in mind that we're moving from a UVM IP environment to an SOC. And in our case, the IP environment is a DMA with a couple of agents driving the DMA bus interface on the one side and interfacing with a memory on the other side. And the SoC, of course, is the mobile SoC chip, which was discussed in DVCon last year. This chip emphasizes the fact that you have multiple CPUs, a bus interface that all IPs use and communicate with each other. And we'll show how this could work, how this actually can be targeted, the DMA targeted in a UVM environment, and then the SoC verifying, reusing the DMA model in the SoC environment. Okay, so how does that work? So we want to model and we want to have these modeling principles. The modeling principles are, consider them a pattern, a methodology, and perhaps there'll be libraries that will assist with this modeling and tool-specific things that will also enable this portability. But from a user perspective, we want to think like this when modeling. We want to have, first of all, the model behavior, the key behavior, which is platform agnostic. It doesn't know anything about the actual platform it will be running on, and it basically describes, it's a model describing a behavior that can be mapped to any platform. And so you have this piece of code that is rarely very specific to the behavior. Of course, the language is very aspect-oriented, and it enables us to extend models to add things that are platform-specific. We want to encapsulate the target-specific implementation, meaning that you most probably want multiple packages for each target and be able to use that package when running on that specific target. We want to maximize solve time decisions. Key thing is that we don't want decisions to be made during runtime, thus increasing the overhead and reducing performance and stress on the system. And we want a separation of target platform concerns in different files. So you will put a package together, you will put a list of files that are targeting a specific platform and another list of files targeting another platform. And as mentioned, aspects for the specific platform will be in one group of files, and the aspects for another platform will be in a different group of files. So this is a pattern which I call PS's configuration mapping pattern block diagram. The block diagram here is just to illustrate how this configuration and mapping is done. And the committee at some point of time would like to standardize on this approach so that all tools support the same pattern. Now, a pattern is one way of doing something. It's a recommended way. It doesn't mean you have to follow this pattern. So on the right side, we are looking at a generic test bench with a DUT. A generic test bench will have a DUT. It will have embedded cores for writing embedded test cases in C or C++, and it will have its VIP external to the DUT, driving the DUT. Think of that as a generic environment that anybody will come along and find these pieces in a test bench for which we want to have a DSL model to drive behaviors on this test bench. Okay, so on the left side, these 4 blocks represent the DSL model. And in this pattern, we want a one-to-one mapping to each VIP instance with what we call an agent or execution agent instance. These are DSL component instances, each one representing a blue box on the right side. So for every VIP, for every core, you're going to have an execution agent instance. These execution agents will have configuration data provided by the user to enable the realization and other things. One can imagine that these agents are configured natively in procedural code and basically can have any configuration data conveniently provided by the user, or they could have relationships between themselves also provided by the user using a native DSL. Now we want to connect these agents to the modeling space. The way we do that, we use resources. So resources are a very natural way to be randomly selected, and you can either lock or share a resource. So for every agent instance that maps to every VIP instance or core instance, we'll have a resource object within a pool mapped to that specific execution agent instance. And you can think of each of these execution agents as a resource. For example, you may exclusively want to run just on core A0, and so you'll lock that resource. Or you could even have multiple behaviors running in parallel on the same core, and they will share the resource. But resources is a very natural way to think about mapping an atomic action that has an executable implementation, an exec block body that needs to run on the target platform. That atomic action needs an agent, needs a core, needs a VIP to run the actual implementation on the specific targeted execution agent VIP. So here we see an example where you have atomic action locking a core of type A, and on that core, all the writes implementing the exec of that atomic actions will happen on the selected core. Okay, so when you lock a core, which is associated with this pool, there are 2 resource objects, and exactly one will be picked, and on that core, we would like these writes to be executed. Same thing when you are implementing your exec body using a VIP API, something like a sequence or virtual sequence to execute the API calls. So your implementation, again, will lock the specific VIPX resource. That means that if the soul chose agent 0, the calls will be with respect to VIPX 0. And we'll understand a bit how that actually maps in UVM, because in UVM, you really just need the path to the VIP within the test. So just like in UVM, we have UVM test top .env .agent. That is the path that we want to be used when activating this API. So these are atomic actions, and they will be in components that most probably will contain just atomic actions. Not that that is required, but that would be a good methodology. And then you have your compound actions using those atomic actions. So this basically represents a typical model in DSL, and this is a pattern for doing the configuration and mapping. So here we start off with a target platform agnostic behavior. And this is a behavior doing the regular configuration of the DMA. And then we have a compound action using the atomic actions in the DMA. A configure A is an atomic action. And what will happen is, in the end, we want to map this to either running on a core or running in a UVM sequence. So here you see what the code would look like. So here just what is happening is we are programming a couple of registers. And this is what the code will look like in C, a write to a couple of registers. And this is what the code will look like in UVM, calling UVM functions, which are specific to the system Verilog code, which will be specific to specific registers or write to a general memory. There are many ways to do this, and that will be a topic for later, where we will discuss in the future how the mapping is done by a tool, but this is very tool specific and shouldn't concern us at this point, how the UVM code will look like and how the C code. Just imagine that these two things can be generated by a tool. So these execution agents that I talked about will require, as I mentioned, a pool. And for each, if we had 4 cores, for example, in a mobile chip, there are 4 cores. We will need 4 instances of execution agents to represent those cores. And in the beginning, I showed that the IP UVM environment of the DMA had 4 BFMs. This will represent the 4 BFMs driving the bus using a UVM VIP, and the selected VIP will be the one that will actually do the work of driving the bus. And of course, as we mentioned before in the previous slides, you would need to set up your memory space. So in the mobile chip, we had a DMA region, a DRAM region, and a flash region. And this is how you would add to the model using extend. You would add the definitions of the memory address space. This is where the user configures, and this is just again to illustrate how it's done. Hopefully the committee will come up with a very standard way of doing this, and it will hopefully use components and not lists to provide the configuration data. But here you see the user needs to say, when I'm using a VIP of some sort, what is its path in the test bench with a string? And UVM has facilities to get things like sequencers or agents given a string. So a string can be mapped to an object very conveniently in UVM, and therefore knowing these paths in a string can help conveniently get access to a specific object in UVM and enable the mapping of a function call to a specific agent, sequencer, etc. Same thing with the embedded environment. The tool that will be targeting to the embedded cores needs to know a topology. For example, if there's multiple clusters and each cluster has a different core, that's information you want to know, and you want to make sure that certain code, when the mapping tool maps the code to a embedded environment, certain code, certain atomic actions within the behavior will be running on cluster 0 core 0, or cluster 0 core 1, or cluster 1 core 0, and cluster 1 core 1. So that's additional example of configuration data you want to provide about your execution agents, so a mapping tool will know how to map it correctly, be able to run on the specific core that that atomic action was selected to run on. And we can give different file lists, one for the UVM environment and one for the embedded C environment, using the same models, DMA functional model, getting it mapped to either IP UVM environment or an SoC embedded core environment. And then user will provide the specific file list to a tool. And you can imagine that we'd also like to mix. We'd like to have two of the BFMs running and driving the bus in UVM, and two actual cores, embedded cores, driving the bus from embedded core running C code. And so we would also like to be able to mix the different target platforms in the same environment. And again, with this approach and this pattern, it is possible. And for example, here, when you share an execution agent, one of the execution agents will be chosen. So the first two execution agents will be, as we said, on the UVM, and the next two will be on the embedded core side. And here we can see usage of the for all to make sure that specific atomic actions will be run on the UVM using 0 and 1, and others using 2 and 3 running on the embedded core. And you can see here that we are using the resource object ID to determine that. So now we want to talk about opposing stimulus that has been provided by different IP owners and enabling the SoC verification team to take those models that were done at the IP level and reuse them in the SoC. Now, a very powerful concept that we have in DSL is flow objects. Using a flow object, IP owners can provide models and make sure that they follow the flow object type, and doing that, these models are reusable in the SoC, and independent IP developers using a type that is mutual between these developers don't need to coordinate anything else between them to get their stimulus to talk to each other. They just need to know the type, and the type of the flow object determines all the attributes that will be used in the communication. But once the agreement is made between different IP owners on the type of the flow object, a model that is used at an IP level for two different IP models developers can be used and compose a system level scenario model. And this is, we're going to give you an example of how this is done. This is what we call a chaining example. And we want to create scenarios where, for example, a packet will come in through the LTE, it will be transferred to memory through a DMA transfer, and will find itself in DRAM. Okay, so this is kind of a chaining, but you can imagine any level of chaining and any number or any length of the chain where one piece of data is moved to from one IP to another IP, and so on and so forth in a system level scenario. This is very powerful. Imagine we can have these things running in parallel. So through these models that I was given by IP owners, I don't need to do too much work to create this system level scenario of parallel chains moving data from one place to another, and in parallel And on top of that, there is no memory conflicts, meaning that this is memory safe because we are using memory allocation. All these chains occurring, moving data from one place to another, are not overriding each other. And from the beginning to the chain to the end of the chain, you can check that the data arrive correctly to the end point of the chain. Okay, you want to know that the data at the start of the chain equals data at the end of the chain, and there was no overriding of that data by another parallel chain occurring at the same time. These are very powerful system level scenarios. So we'll start off with our system level definition. So we're getting all these IP from different IP owners. For example, DMA, LTE, display. We set up our resources for our execution agents, as mentioned in the pattern in the previous slides, and we set up our memory space. So how do we do this chaining from multiple IP through memory buffers? So we want to have, as I mentioned, we want to have a flow object type that is used in common between all IP developers. We want to create these chaining structures, and these chaining structures can be of any complexity. They can be sequential, so moving data from one point of memory to another, and then from that point to another point of memory. Or we could have multiple of these chains occurring in parallel, or we could have any arbitrary graph structure of how these data goes from one point to another. For example, a data could go from point A to point B, and then from point B it can go to point C, or you could have from point B going to point D. So you can imagine any arbitrary structure of moving data in the system. And the more arbitrary, the more complex and the more interesting scenarios are created. We use the address core library from the standard to enable data integrity, meaning that no data, you have this parallel data moving from one place to another, they're not stepping on each other. And we're also interested in the coverage. How well did I cover the different IPs and the different memory spaces when doing this chaining? Those are the considerations. So the common flow object, of course, it can be a buffer, and the buffer has the memory space, which is exclusive when outputting data into a certain memory place. Then we have the action memcompa, which enables taking input and providing output. Okay, so this is a package that everybody is working with. All IP developers have this package, and it has the type of the flow object so that all actions that will be involved in the chaining will use the same flow object, and all actions involved in chaining will inherit. And not everyone has to inherit the memcopy, but the memcopy A is a very convenient action to inherit because you don't need to write input-output again and again for the many actions that you need to implement. So if you look at it here, this is the IP owners' plans, right? Now, IP owners need to think about what is input, what is output, and what is something that needs memory to memory. So the LTE modem has external VIP, so it has a source. So you need actions that will take external VIP and drive output to the buffer. And then you need actions that will go from the memory, internal memory, to the external VIP, and then doing a loop back with the external VIP back to memory. So those will be memory to memory actions. And then you have sync actions that will output the data to external VIP. And basically in the chain. So a chain starts from a source, okay? Then it does multiple memories to memory, and then it has a sync. And each VIP is either providing sync actions, source actions, For memory-to-memory actions, okay, here you can see the DMA is taking one piece of memory and transferring to another. CPU can do the same, can read memory and write memory. Okay, so there's many ways of creating these chains using the IP owner's stimulus that they provided, using a source, memory-to-memory, and sync actions. And this is what the IP owners will provide. This is like kind of a template. They'll provide, based on the device, the source, the memories to memories, their sync actions. Okay, sync actions need an input, source actions have an output, and memory to memory have both inputs and outputs. And the inferencing of the system level scenario will figure out how to bind these actions. And so the user doesn't need to write specific directed behaviors. You can let the tool figure out the behaviors from IP to IP through memory without writing a complex scenario, directed scenario, and trying to cover all the cases, right? We want to do random generation of these chains and then perhaps figure out the coverage achieved by the different chains and reduce the overhead of doing very directed tests that go through specific IP to achieve a chain. So here, for example, we show how conveniently it is to create a sequential chain. So we always want to start from a source. We want to have a memory to memory, and then we want to have a sync. So we randomly select, be weighted among the available source actions provided by the IP owners, and then we randomly select a memory to memory action, and we could have as many memory to memory actions as we like. Here in this case we have 2, but we can think of ways how to randomize the number of memory to memory actions, and then we need a sync. So here showing one example on the right where a LTE modem is taking data from the external VIP, putting it in DRAM, then using a memory to memory, taking at the DMA action, moving it to another location in the DRAM, doing another DMA, moving it to another location in the DRAM, and then moving that data to the display. And here you can see the graph showing how the actions execute at one action, moving data through a buffer, and the ordering between the actions. So that would be one scenario generated for the specific DSL on the left. And then we could have parallel chains independently running and using the parallel replicate. Parallel replicates expands this into 2 chains that are running in parallel. And they will just reuse the previous slides, single sequential chaining. And so you can use the parallel, and this works well because the buffer pool will have independent buffer objects, each used by different chaining threads running in parallel. And we want to make sure that they don't share the same buffer objects because, as you know, parallel behaviors cannot interact with each other. They need to be strictly parallel, so therefore they cannot have buffer dependencies in between them. And so that buffer pool is very convenient because you can have a buffer object at any time per thread. And here you can see an example of how we would use coverage using a cover group that has a cover point. And here basically we want to see that we covered all the scenarios with a source, 2 mem-to-mem actions, and a sync. And then so basically you can provide this every time there's a mem-to-mem action, we can have an attribute saying what the source ID was of that mem-to-mem action. And that will be recorded in the coverage. And here you see the association between an enum representing the mem-to-mem and the actual chain. So here, mem-to-mem ID 0 will associate with mem-to-mem ID 0 here, this attribute. This is an inline cover group and has access to this attribute. So overall, we gave you one example on how to compose these very complex system-level scenarios. That was just one example. One can imagine any level of complexity where an IP owner will provide a scenario that can be reused in a very generic fashion in the system level and make sure that resources are exclusive, memory is exclusive, and so these different scenarios, even though they weren't planned up front to work together, not stumbling on each other's resources or memory space, the capabilities of DSL and the languages and DSL semantics enables this very easily to put these scenarios together and make the tool figure out what to do in order for these scenarios not to stumble on each other and override each other's data, or use a resource that is needed exclusively for an action, use those simultaneously. Okay, and with that, I'll pass the presentation over to Tom to do a high-level summary of the overall presentation. Thank you.
Okay, so just to wrap things up, so the key points for today: consistent specification of your intent throughout the process. Methodology portability saves time and resources. It is a shift left enabler because you're starting to do more upfront at the abstract level and allows you to develop some of your test content in parallel and reuse and scaling across the verification, as Matan just mentioned. So there's lots more that we could talk about with this. When I'm asked to do a tutorial, it's much easier for me to do a full day tutorial than a half-hour tutorial or even a couple hours. So, we were joking about the 3-day tutorial version. There's probably going to be something like that coming out eventually. But for now, I hope this gives you a good overview of kind of our objectives in defining the standard in the first place, particularly some of the new stuff we've added in 1.1. We expect that there will be a public review version of 1.1 available before we actually have the standard approved. So you'll all get to take a look at it. Our hope was to give you kind of a jump start on that to illustrate some of the more important concepts in 1.1. So when you actually do get the public review, you can actually look at it and provide meaningful feedback for us, because that's a valuable part of the standardization process. Then once we do that, then we'll roll out 1.1. So the schedule for when 1.1 is coming out is still a little bit up in the air. There'll definitely be some more updates at DAC, and DVCon Europe is coming in the fall. So please stay involved. And again, if you're interested in joining the work group, you're more than welcome to. So thank you very much.